In this video, we'll look at soil properties. Note that Moodle has additional written resources on water content density and bearing capacity that provide a more detailed description of these concepts. It is recommended that you review these written resources as well as viewing this video. There are three basic soil groups to be considered in earthworks. These are coarse soils, fine soils, and organic soils. Coarse soils are sands and gravels, and they may be referred to as granular, non-cohesive, or cohesionless soils. Coarse soils are derived from only mechanical weathering and usually have the material properties of the parent rock. A coarse soil mass is held together solely by the friction from particle-to-particle connections. The properties of this soil is mainly influenced by the particle size distribution. Fine soils are silts and clays. They may be referred to as non-granular or cohesive soils. Fine soils are usually the result of mechanical, chemical, and biological weathering, so the soil properties usually vary significantly from those of the parent rock. The chemical weathering, in particular, changes the soil particle properties, so there is an attractive force between soil particles. This attractive force is called cohesion. The strength of a fine soil is derived from both the cohesion and the friction between the soil particles. The properties of fine soils are mainly related to their water content. Organic soils may be called topsoil, peat, or loam, or other things. They are usually formed on the surface of a soil formation, but some soils may have organic material layers or content deeper down. These soils have significant amounts of organic material from the decomposition of plants. This organic material can swell and shrink dramatically according to the water content, and also usually result in the soil being quite soft. Therefore, organic soils are usually not suitable for road formation, but they may be used on berms or in non-structural fill. Soils that do not have organic content may also be called inorganic soils. Inorganic soils are usually categorized by the size of their particles. Gravels have particles from 60 millimeters in diameter down to 2 millimeters. Sands have particles from 2 millimeters down to 0.6 millimeters. 0.6 millimeters is the same as 60 micrometers. 1 micrometer is 1 millionth of a meter, so 60 micrometers is about the width of a human hair and is the limit of human vision. Most people cannot see particles smaller than 60 micrometers. So if you can just see the soil particles, then the soil is probably a sand. If you cannot see the soil particles, then the soil is probably a silt or a clay. Silts range between 2 micrometers and 60 micrometers, while clays are composed of particles smaller than 2 micrometers. This slide shows the sizes of each soil type. The boxes show the hatching that is used in reports and drawings that are used to show the distribution of soils. A soil may also be a mix of soil types. In this case, the soil descriptor includes both of the types present. So the soil with mostly sand but a little bit of silt would be a silty sand. If it had more silt than sand, then it would be a sandy silt. Soils are composed of solid soil particles with voids between them. These voids may be filled with air or water or both. Therefore, soil is composed of three substances, mainly solid particles, water, and air. These are referred to as the phases of a soil. A soil with the voids completely filled with water is said to be saturated. A saturated soil is a two-phase soil because it has only two substances present, solids and water. This is the normal state of soils below the water table in a soil. A soil that just has solid particles and air without any water is said to be dry. A dry soil is defined as a two-phase soil because it only has two substances, solids and air. Soils with both water and air in the voids is a three-phase soil. This is the normal state of soils above the water table. The amount of the soil structure that is voids is called the porosity. It is a measure of the volume of the voids divided by the total volume of the soil. So here the voids are shown in yellow and the total volume is shown in the green line. So the total volume includes the volume of the voids and the volume of the solid particles. For example, the porosity of a well-graded gravel soil would be around 0.3, which means that the volume of voids is 30% of the total soil volume. Most soils have a porosity of between 0.2 and 0.4. Soils with larger soil particles, such as sands and gravels, have bigger voids, while silts and clays have a larger number of smaller voids. The amount of water in the soil is called the water content. It may also be called the moisture content. The water content is determined by dividing the mass of the water by the mass of the solids in a soil sample. Note that the water content is measured by weight, while the porosity is measured by volume. Also, with the water content, we're only looking at the mass of water compared to the mass of the solids, not the total mass of the soil. The properties of soils of silts and clays vary according to the amount of water in the soil, so the water content is a very important measure. As the water content goes up, the soil gets softer. We also need to have the water content at a certain percentage when we compact the soil to enable us to compact it to its maximum density and strength. So knowing the water content is essential for earthworks. Water can flow through the soil via the voids. The rate at which the water can flow through the soil is called its permeability. Permeability depends on the porosity, or volume of the voids, and their connectivity. In other words, how well they are connected. Gravels and sands have higher permeability, while silts have less permeability, and clays have very low permeability, sometimes no permeability. In other words, water cannot get through it. When we compact the soil, we reduce the void volume, so the permeability reduces after compaction. Permeability directly impacts the drainage of a soil. So rain falling on the soil either infiltrates into the soil, as shown by the light blue line, and moves through the soil structure to the water system, or it flows over the soil surface, as shown by the green line. Water infiltrating into the soil is called groundwater. The water that flows over the surface is called runoff. So the green line there is the runoff. The light blue line there is the groundwater. Typically, 80 to 90% of rain falling on loose gravel will soak into the soil, with only 10 to 20% flowing over the surface. In other words, 80 to 90% becomes groundwater, while 10 to 20% becomes runoff. However, only 30 to 40% of rain falling on bare clay surface will infiltrate into it. The rest will flow over the surface, or it will pond if it cannot flow. Density is the degree of compactness of a soil. It is measured by the volume of a soil divided. It is measured by the mass of a soil sample divided by its volume. Therefore, the density of a soil is usually measured as kilograms per cubic meter or tons per cubic meter. This slide shows a 1 cubic meter sample of soil which is being weighed. The sample weighs 2,050 kilograms, which means that the density of the soil is 2,050 kilograms per cubic meter. If we compact the soil sample, then the volume will reduce as the solid soil particles would be pushed into the void spaces. This results in the density increasing as there is the same mass of soil in a smaller volume. The denser soil would also have more contact points between the soil particles. The soil strength is derived from the contact points between the soil particles, so a compacted soil would be stronger because there are more contact points. So increasing the density increases the soil strength. That is why we compact the soil. There is more information on density in the Moodle notes. The strength of a soil is usually referred to as its bearing capacity. The bearing capacity is the pressure that a soil can carry without failing or deforming excessively. Pressure is force applied over an area and is measured in kilopascals. 1 kilopascal is the pressure that a 1 kilonewton load applies over a 1 square meter area. Let's put that in real terms. A 100 kilogram person exerts a force of about 1 kilonewton on the Earth's surface. If that person was standing on a 1 meter by 1 meter square of, say, plywood, then the plywood would be exerting a pressure of 1 kilopascal on the ground beneath it. That is, it has a 1 kilonewton force applied over a 1 square meter area. The ground under the plywood either resists this pressure or it settles to a higher density which can resist the pressure without deforming. Applying this to roading, we do not want the soil under the road to deform, as that will result in the road pavement also deforming and creating bumps and depressions in the road surface. So, the soil needs to resist the loading without deforming. This slide shows a truck axle applying a pressure on a road surface, which is shown as the grey shaded surface. Beneath the surface is the base course and subbase, which are layers of well-compacted sandy gravels, which are able to resist these surface pressures. Most soils would not be able to resist the road pressures, which is why we have the base course and subbase. The base course and subbase distribute the pressures as they distribute them down to the soil, as shown by the dashed lines on the slide. Distributing the force over a large area reduces the pressure on the soil. The pressure at the soil surface needs to be significantly less than the soil's bearing pressure to ensure that the soil will resist the pressures on it without deforming in all conditions and over a long period of time. As mentioned in the previous slide, the bearing capacity of the soil can be increased by compacting the soil as that pushes the soil particles into a more dense arrangement that better resists pressure because there are more contact points between the soil particles. The bearing capacity is usually measured by the CBR or California bearing ratio. Bearing pressure and CBR are discussed in more detail in the Moodle notes.